Hello everyone. So, we will continue with the sampling of textile material. So, last class we have discussed the broad classification of sampling. It is broadly classified into two categories, one is numerical sampling and then another is biased sampling. Biased sampling is mainly it is a length biased we will discuss, and causes of biasness we have discussed. It is due to physical characteristics of material, position of relative to the person, subconscious biasness and conscious biasness, this we have discussed. Now, we will start with the terms, various terms related to sampling. So, commonly used in the industry. Okay. Terms, first term is consignment. One must understand this difference between these terms. A consignment is that it is a delivered item at a time, okay, and it may consist of several lots, like, and it is delivered from a particular supplier to a particular buyer. It is called consignment. Suppose one supplier is supplying 10 tons of yarn of 20s count, 5 tons of 30s count, say another 10 tons for say 50s count, like that. This is order from a particular supplier, and he is supplying this order to that the customer at a time. So, this total 3 different lots he is supplying, one is of say 20s count, another 30s count and 50s count lots he is supplying at a time. Once it is going at a time, maybe say 10 containers, once it is going at a time, then it is called one consignment. Similarly, for fabrics also, for different types of design, if it is going from one supplier to a particular customer at a time, that will be one consignment. And say yarn 20s count, 30s count and 50s count, they are going together as a consignment, but this 20s count yarn, total 20s count, it is called lot. Okay. And this test lot, is statistically it is a population. That means, one particular lot when it is coming at a time, same time or batch, it is totally statistically it is population. That means, the test lot or batch, it consists of all the containers, say 20s count, it has got say 6 containers. So, this 6 containers, all the containers of definite type and quality, same quality, delivered to one customer at the same time, that is called the lot. If the same material is going in other day with other consignment, that will be considered as other lot, okay. That is a lot, and one lot is taken as whole population as per statistics. So, the population does not mean the entire material which that customer has received throughout the month, it is not that. In a particular day, in a particular consignment, whatever material is coming in a lot, that particular lot is known as the statistical population. Okay. Then what is laboratory sample? So, we have seen the consignment, we have understood the lot. The laboratory sample is that using the statistical sampling technique from the lot population, if we take the sample, that is called the laboratory sample. we are used it is derived by the appropriate sampling method from the test lot. Test lot means the whole material, it is a part of the consignment and will be used as the basis of the testing in the lab. This sampling we are doing only for testing in the laboratory, that is why it is called laboratory sample. And from the laboratory sample, say we have got say such 50 bobbins and or say 500 gram or 100 gram of yarn fiber, loose fiber, and from this loose fiber we need say this much material for say fiber fineness measurement. Actually it is used for fiber fineness measurement, or this much material fiber is used for say length measurement. So, this is the actually the fiber is used, this is called the specimen, it is called the test specimen, which is derived from the laboratory sample and is actually used for the measurement of the parameter. So, consignment, then test lot, then laboratory sample and the test specimen. So, for testing one must know these terms, okay, to avoid any confusion. And sampling, the significance in the textile material, why sampling is important in textile material, as we have mentioned, the only reason is that the sampling of textile material, fiber, sliver, roving, yarn, fabric should be representative of the bulk, okay. And sampling technique assume utmost importance, because the textile material is highly variable in nature. So, for other material, other product where specific shape is produced, their sampling is not that important. One can use randomly some material and test, but in textile material, as it is highly variable. So, we must follow specific sampling technique. Now, coming to the sampling of textile material. Okay. First, starting with the cotton fiber from bale. So, cotton comes in the bale form, okay, and sampling of cotton has to be carried out at 3 distinct stages. If we talk about the sampling from bale, first is that sampling from bale, it is called bulk sample. First we have to take bulk sample, then from bulk sample we have to collect the basic sample, and from basic sample we have to collect the laboratory sample. These are the 3 stages of sampling of cotton fiber from bale. Now, bulk sample, what is that? When a large number of bales of cotton belonging to a particular variety, suppose we have got say 100 bales, okay, particular is purchased, a few bales may be chosen at random. So, this selection has to be based on the random number. So, few bales we are selecting as by random numbering, okay, as representing the bale. Okay. So, the bulk, this few numbers, say 10 bales we are selecting, these are actually representing the bulk, and the numbers of sample, there are some standards. If our bulk size is say 50, we can take 2 bales, we do not have to waste the material, 2 bales at random. So, 51 to 100, then 4 bales, like that. So, 1000 and above, so 40 bales we have to select random. This is the standard sample size. Okay. And then bulk sample, what we have to do? We have to draw handful of fiber from different portion of the bell. So, we just open the strap, take samples, bulk samples from top, from center, from bottom, different randomly, which will be representative sample. Okay. After that, so that bulk from the, say, suppose we have in the consignment we have 100 bells. So, we have selected 4 such bells and we have taken the bulk sample randomly from 4 bells, and then basic sample we have to the tufts of fibers from each bell may be mixed up thoroughly as to form homogeneous representative of sample. So, from each bell, whatever from different tufts from particular bells we have taken sample from top, bottom, center, and then we mix the sample to may have homogeneous mixture, and from there we take select sample. From each bell we select and proper homogeneous sample from all the bells chosen at random. Okay. That is the basic sample we have prepared, and total quantity of basic sample prepared should be around 1.5 kg, 1 kg. So, that we have total quantity from different bell. So, if we have say number of sample, number of bells is 40, then accordingly we have to take smaller quantity. If we have say 2 bells, we have to take say 500 gram plus 500 gram, like that. Total basic sample quantity is roughly around 1 kg. So, basic sample is there. So, they are separately mixed, and depending on the number of bells, it is basic sample is prepared. Then after that, to have laboratory sample, to find a sample in which the test has to be carried out is called laboratory sample. As we have already mentioned, the laboratory sample is drawn from the basic sample. So, from those homogeneously mixed sample, so that basic sample has to be prepared and derived into several equal parts. Okay. And from each part, now here normally we use the zoning technique. So, laboratory sample is prepared, then we take from each part small tufts of fiber is drawn, and then all these tufts are mixed together to form a small sample. So, the technique is used here is typically it is called the zoning technique, and for all this maturity, HVI, all these characteristics, and example is zoning technique. We may use, I will discuss the zoning technique here. Using the zoning technique, one can get the laboratory sample. Okay. Before going to the actual sampling of fibers or yarns, let us try to understand the concept of critical difference. The critical difference is measured, it is a measure of difference between the two values that arises solely due to natural or unavoidable causes. It is due to natural cause, okay. That is called critical difference. When the difference between two values exceeds this critical difference, then we can tell it is a statistically different. Okay. And these values are based on the recommended number of tests for which for each fiber or yarn, that is given in table. I will show you the table. So, for the for a different type of test different type of test result, the critical difference values are given, like see, these are the standard tables available. Like for 2.5% span length, if we want to get the critical difference, so number of tests required 4 such combs. The sample for fibrograph is called comb. Okay. Fibrosampler produce the sample in the form of comb, that I will discuss So, at least 4 combs per sample should be there, and critical difference is that 4%. If the span length 2.5% value, span length value is more than 4%, then the critical difference is, its actual difference is existing, significant difference is there, that we can tell. For uniformity ratio, again 4 combs per sample, it is a 5. Micronear value, 4 plugs per sample, it is a 6, like that. This is the for trace content, 8 tests per sample, 7%. And micronear value, this is the value 6%, just to remember the 6%. I will give you one example in next slide, so that it will be clear. Okay. I have taken only one example for micronear, just to show the significance of critical difference. For Lee count 40 test, this one 2% CT, like U percent 10 test, it is a 5. Okay. Double yarn twist 50 test, it is a 2%. These are the critical difference, tabulated critical difference, and we have to calculate the difference based on the particular number of samples. Now, try to see the example here. A cotton is tested and it has got 3.4 and 3.6 values. Now, we have to see whether these 2 cottons, they have got the difference is exactly statistically significant or not, whether this difference is other than the chance factor or not, or natural variation or not. So, critical difference actually gives indication of the natural variation, because textile material, they are naturally variable. Because this I will come back, I am going back to the slide again. So, this 4%, its span length variation is due to the natural variation, that has to be there. We cannot go beyond that. Okay. That is how the, it is based on the experience, that this data, there is no, it is based on the statistics. Okay. So, 3.4 is there, and another test it is giving 3.6 value. Now, we have to take decision whether this difference is statistically significant or not. The percent difference is expressed as 3.6 minus 3.4, that is the difference, divided by the mean and expressed in percentage. Mean is here 3.5, 3.4 and 3.6, mean is 3.5. So, difference is 5.6, but the tabulated value which we have seen earlier, it was 6%. So, which is less than that. So, that means we can tell this difference is natural, it is not due to other reason, there is no statistical proof that the difference exists. And also the number of tests, I will go back once again, say number of test is say 40, number of test here it is a 40, number of test here it is a 100. Sometime it may not be possible due to various reason, that many samples test is not possible, or sometime we may not stick to 40, we may go beyond that 50. In that case, we can recalculate the critical difference using this formula. The recommended number of tests are not performed, it may be less or more, the new critical difference can be computed. We can, that is critical difference new is that this is the tabulated critical difference multiplied by n1 by n2 under root n1 by n2, where n1 is the recommended number as per table, n2 is the test actually number of tests carried out. So, using this formula one can calculate the modified critical difference and then compare the see the whether the test material significantly different or not. Okay. The accuracy of the test data depends upon the number of tests carried out. That we will discuss separately. If we take the number of sample more the sample, the confidence level will be more and accuracy will be more. Now, we will start with the sampling of textile material. First, the sampling technique, it is the from bulk we have to take the laboratory sample, and for cotton the sample which is the technique which is used, it is called zoning technique. Now, zoning technique, it is not in any specific technique, it is a idea, there is no specific rule, one can formulate the rule, then one can go ahead with this. And I will explain one such norms, one such rule which is flexible. Okay. Say taft of sample from at least 40 zones has to be there. Okay. So, 40 zones one has to create. So, take a specific proportion from each taft to make the final sample, looking one free from any damage. Okay. So, free from any damage, you take the sample from the bulk, a sample of sufficient quantity, say about 100 gram we have to prepare, is prepared by selecting about say 80 large taft chosen as far as possible over the bulk. So, different tafts we have selected, divide this sample into 4 quarters. So, 4 quarters it has been divided, take 16 small tafts at random from each quarter, the size approximately 20 milligram. So, from each quarter 4 quarter we have divided, and then from each quarter we have taken 16 small tafts. So, how much taft we have got? We have got say 64 tafts. Okay. Each small taft shall be halved several times, like this is small taft. So, I am taking this one and discarding this, then I am rotating again right angle and again I am discarding from this. In this way we have to several times we have to take the halves. Okay. Discard alternatively with right and left hand. So, we have to discard the sample and keep on reducing the quantity, and after each taft discarding, then we have to rotate it. So, that you are again randomizing, okay, turning the taft through a right angle between successive halving. 16 wisps are thus produced from each quarter of the sample. So, this 16 wisps, that is 4 set of 16, that is 64. Combine each set 4 set of wisps into tafts. So, we are getting 4 tafts we are getting. Mix each taft in turns by doubling and drawing. So, by doubling and drawing we have to mix the taft between fingers. So, we have to again, so tafts we have to mix like this, doubling and drawing. Divide each taft into 4 parts. Okay. Obtain 4 new tafts by combining a part of each of former tafts. As for example, part 1 of taft 1, part 1 of taft 2, part 1 of taft 3 and part 1 of taft 4 are mixed together. Similarly, part 2 of taft 1, part 2 of, in this way we are mixing, mix each new taft, 4 new taft again by doubling and drawing. So, in this way zoning technique will continue. Take a quarter from each tuft, go to, and then we are making the final sample. So, then quarter from each tuft by again discarding we will get final sample, and that was a different sampling technique, zoning technique. One can have another simplified zoning technique. Okay. This animation will tell. Here we have taken from different bells, tufts from different bells, okay. Basic samples from different bells we have taken, and after that we are dividing into two part, discarding one part, and again it is dividing into two part, discarding one part, this is one part it is coming, and then finally after several time repetition we are getting this final value, final stuff, and then we mix these things together, and this is called zoning technique, because we are using from different zone we are trying to take, and after discarding every sample we are rotating it again. Now, this animation will give idea. Try to see, these are the initial sample. Now, it is dividing into two halves, red one we have to reject. So, we are discarding, and rest half we are taking. Okay, this is discarding, and this again we are dividing into two parts by rotating, okay, 90 degree. Again it is a we are discarding. In this way amount of fiber, number of fibers are reducing, quantity of material is reducing, and ultimately the final quantity will be the addition of all this. So, this is the if we know our required number of fibers or required quantity of fibers, so we can continue up to that point. Suppose we have say x number of n number of this zones, n different zones are there, and say 20 zones are there, and we require say 100 gram of fiber. Okay. So, then each zone we should continue up to the point where each zone will have say 5 gram of material. So, to mix all this we will get 100 gram. So, this is zoning technique which is very simple one, and zoning technique there is the advantage is that there is no specific rule of zoning technique. One can formulate zoning technique on his own for the industry. Okay. Next is that wool sampling from the bale, and which is very important for wool fiber, because the wool raw fiber it is highly sticky, and to get fiber from the bale it is not so simple, it is not easy, because it is a highly compact. So, we have to take fiber from the, we cannot open wool bale so easily. Okay. We have to take the lump from the surface and then only we can open. It is not, it is very difficult to take sample from the center of the bale. So, the core sampling is used. So, it is used for assessing the proportion of grease, vegetable matter in the sample taken from unopened bale of raw material. So, it is basically used for to measure the grease content, and to some extent we can test the diameter, but we cannot test the length of the fiber, because here it consists of a cutting tip. This is the tube, coring tube, this, and through this cutting tube it penetrates this, and here this is the plastic bag just to store the material, and the slit is there, enable the core to be ejected by core ejector. Okay. Core has to be ejected. Okay. So, this it consists of this tube and cutting tip. Now, the coring tube length, it is approximately 2 feet length. So, if we see the wool fiber bale, it is typically 4 feet, its total height is 4 feet. So, it is 2 feet because if it penetrates, it is reaching up to the center, okay, the halfway into the bale, that is sample from the center we can take. The tube penetrates in the direction of compression, because the fibers it does not penetrate vertically, it penetrates directly where the compression side is there. So, perpendicular to the layer of fibers it penetrates. The cutting tip diameter is less than the coring diameter, this cutting tip diameter is less than the core tube diameter. The advantage is that it helps the sliding of core, core means the cut wool fiber by the cutting tube. When it penetrates, when it is pushed, the fibers are cut, it forms a cylindrical core. The core diameter is equal to the cutting tip diameter, which easily penetrates inside the coring tube. That is why this diameter is smaller. Another advantage is that it helps retaining the core as it is withdrawn. So, because when the material, when the wool that coring tube is withdrawn, the core should be inside the coring tube, it should not come back. So, as it is smaller in size, after penetrating the core gets expanded, and so the coring tube when it is withdrawn, the core is or remains in the coring tube. The number of cores are extracted and combined. So, there will be a number of cores will be extracted and they are stored here. So, each core will have certain quantity, and after that the core is actually transferred to the this plastic bag. Okay. Different size of tubes are there, this type 14 millimeter, 15 millimeter, 18 depending on the type of wool. After removal, the cores are kept in airtight container immediately. So, this is the polythene bag. So, after that core is taken, and then it is a airtight container is there, because otherwise wool will absorb moisture and total characteristics will change. So, we do not need to open this polythene sheet, polythene bag, so that it should not get exposed to the environment. And hydraulic coring machine is there for large number of sample. Coring machine, that its automatic hydraulic pressure is there, so it penetrates automatically. Now, let us see the animation here. This is the coring tube and it is a bale of wool fiber and it is penetrating. It is penetrating inside, and this is one core has been withdrawn. Okay. And this tube is full of the core, so that you have to remove this core. So, you take it is vertically, it is a, then this core will be stored here. Okay. And another core then we keep on repeating. until and unless the required quantity of material is collected. So, next core is there. So, this is the coring technique. Okay. Now, here one important thing is that this coring tube is cutting the fiber. The coring tube, this due to this the tip, it is cutting the fiber. So, we have to select all, we have to test those parameters only which are not actually dependent on the cutting of the fiber. So, we will not definitely test the fiber length, we will definitely we will try here it is used for grease content, which is very important, which does not actually depend on the length, whether it is cut or not does not depend. Okay. And to some extent this coring, this sample is used for the fiber diameter, but from long fiber also one can measure the fiber diameter. Now, fiber sampling from sliver, roving or yarn. It is very difficult to obtain unbiased sample, because unless special precautions are taken, longer fibers are more likely to be taken by the sampling procedure, leading to a length biased sample. So, as I have already mentioned, so if we try to take the sample from the bulk also, if we try to pick the sample, we are actually selecting the length biased sample. Even for this sliver, if we try to pick, we are trying to take the length biased sample, because longer fiber will have chance, more chance, higher chance to be selected. So, there are two ways of counteract this problem. One is we can prepare the numerical sample, which is actually different from length biased sample, which is unbiased sample. Another way is that to prepare a length biased sample in such a way that the biasness can be allowed to do away with, do any calculation based on some assumptions. So, there will be some assumption. So, first we take the length biased sample and then we can calculate based on the knowing the fact it is a length biased, and then we can assume some assumptions. Okay. First we will discuss the length numerical sampling. Now, in this numerical sampling, the remove all the fibers which are started at left of the line A. This is the sliver, suppose it is a sliver, we are trying to discuss this is the sliver. So, in the sliver, suppose it is a, we have drawn so imaginary line A, B, C, D like that. Okay. First we decide, we take all the fiber which are at the left side of the A, line A. So, we have taken out 1, 2, 3, 4 fibers. Now, this removal of these fibers is not affecting the fibers which have end point at between A and B. So, removal of all fibers which are started left of A point, the other fibers will be unaffected, total unaffected. So, if we remove all these fibers, other fibers will be unaffected. Again, removing the fibers from zone A B, this zone, that with the green pointed fibers, if we remove all these fibers, the other fibers will be unaffected, like red pointed and black pointed fibers will get unaffected. In this way, if we keep on taking the fibers, there the longer fibers, whether fibers are longer or shorter, they have got equal opportunity. So, the numerical sample is taken from the end point of any parallelly arranged fiber strand, but we cannot draw numerical sample from a fiber tuft, randomly oriented fiber tuft we cannot draw a numerical sample. Here wherever we try to take, it will be the length bias sample, but in a parallelly oriented sample it may be roving, may be sliver or may be yarn. If we take the fibers sample from the end point, we are taking the fibers irrespective of the length. Here the length of the fiber is not coming into picture. So, both short fiber and long fiber, all the fibers irrespective of the length will have equal opportunity to get selected. So, that is why it is a numerical sample. Okay. If the removal of one sample does not affect the composition of the remaining samples, then it can be considered as numerical sample. That means, if we remove this all the fibers left of which start end point at the left of B, this will not affect the composition of other fibers. So, that is why here it is a length unbiased sample. Okay. And what is length bias sample? In length bias sample, the samples of higher length will have the chance of getting selected, more probability of getting selected. And in length bias sample, this is the equation x I is proportional to the x L y multiplied by y, where x I is the proportion of I length group in sample. So, this is the proportion of I length group in the sample. If we take the length bias sample from the bulk, so I length group, there are different length group 10 millimeter, 20 millimeter, 30 millimeter length group. So, I length group. So, this is the proportion of the I length group in the sample, and L y is the length of fiber with proportion y% in bulk. Okay. So, this is the, and ultimately this the proportion in the sample is totally different from the proportion in the bulk. So, one example is that L y is the, what is L y? Is the length of fiber with proportion of y% in bulk. So, this is the bulk proportion. So, let us say in bulk it is a mixture of fiber length of 3 groups. So, 10 millimeter, 20 millimeter and 30 millimeter. Okay. And there are various other groups are there, other fiber. So, 15 millimeter, 25 millimeter. So, 10 millimeter it consists of 15% of the in the bulk, 20 millimeter the fiber is 15% in the bulk, 30 millimeter 15% in the bulk. So, in the bulk if we see, it means, so 10 millimeter, 20 millimeter, 30 millimeter are equally mixed in the bulk, but when we take the length bias sample, suppose here this is the tuft, from tuft we cannot do the numerical sampling, we have to do the length bias sampling. So, from tuft, suppose in this tuft it is a mixture of say 10 millimeter, 20 millimeter, 30 millimeter, say 15% fibers are there, or other lengths are equally say are at different proportion. Now, here if we see, if we take the sample, what will be the proportion of the length biased sample in the sample as per the length. So, 10 millimeter fiber for length, what the proportion here was 15%, but in the bulk, in the sample it will be 150, because it is a multiple of 10 multiplied by 15. So, it is 150. Similarly, 20 millimeter fiber, its proportion is 300, 30 millimeter fiber, its proportion is 450. So, if we take the actual proportion in the sample of this fiber, the short fiber, that is a 10 millimeter fiber is to 20 millimeter is to 30 millimeter, it is a 1:2:3. What does it mean? In the bulk, the sample proportions were same, 15% each, that means 1:1:1. But when we are sampling, we are taking the sample, its proportion has changed depending on the length of the fiber. It has, its proportion has become 1:2:3. That means 30 millimeter fiber has got 3 times probability to that of 10 millimeter fiber due to the length. So, that is the length bias sampling. Okay. So, it is a multiple of the fiber length and the proportion in the bulk. And if we remove, say, if we remove the length bias sample, in the bulk the 10 millimeter, 20 millimeter and 30 millimeter was 1:1:1 equal, but if we remove 1:2:3 fiber, that means in the bulk the remaining portion, here the total proportion will change, because here in the bulk, in the sample we have taken more longer fiber. So, longer fiber proportion will reduce here. So, removal of length bias sample will change the proportion of fiber in the remaining bulk, as the longer fiber will be removed at higher proportion in the sample. Okay. So, this changes the characteristics of the bulk, but in numerical sample it does not change the characteristics. Like I am taking numerical sample from this sliver in this way. So, bulk characteristics remain same. Okay. And the length bias sample, the chance of fiber crossing the line A and B is proportional to its length. So, this is the these lines within this zone, the chances will be more for longer fiber. So, random tuft sampling. So, this is the length bias sampling, and if by some way the fiber crossing in this area between A and B we can select. So, fiber crossing between A and B zone, if we can select, then it will be length bias sampling. Okay. So, the longer fiber will preferably be selected. Okay. So, if we see it is a numerical sampling, in the numerical sampling it is a proportion is same, okay, long fiber and short fiber, and in length bias sampling if we see the length will be little bit high. It will give us the idea of a longer fiber towards the higher length. And then, so how will you prepare such sample? So, length bias sample, how to prepare this length bias sample? So, numerical sample we have discussed, like if we draw the fiber from the edge from a parallelly arranged fiber strand, that will be numerical sample, but length bias sample we can prepare by fibrosampler, which is used in fibrograph, where this is the fiber tuft form and one clamp is there. Clamp is moving through the fiber and it clamps, it takes the fiber, it picks the fiber and it picks the fiber from different point. It is not the it is taking the fiber from the mid base end point. Now, try to see in fibrosampler, fibers are arranged in this fashion. These are the fibers, and what fibrosampler is doing, this is the fiber, it is a clamp, it is moved through the fiber, okay, and the fibers are actually selected are caught at different point. Okay. So, this is in random one. So, this is suppose a clamp, this fiber is gripped at this point, another fiber will be gripped say at the end, this way at different point it is gripping the fiber, okay, at random point, and after that what will happen, this will have folding, this end will not be remaining here, this will remain, this will fold. So, ultimately this will be like this. Now, suppose all the fibers they have equal length. I am trying to take say sample of say polyester just for trial. Okay. Now, this fiber will this clamp will grip the fiber at different point. So, this fiber is clamped at this point, okay. This fiber is clamped at this point, this fiber is clamped at the end point, this fiber is at the middle, this fiber is at the this point say like this. Okay. Now, after that the third one point is that so fiber 1, 2, 3, 4, 5, fiber 1 will get folded, okay, by the clamp in the clamp. So, due to its flexibility it will form a loop like this. This portion becomes here, comes here, this is the portion, and this portion remains here, longer portion. This fiber is selected at this point, at almost at the edge. So, this will form smaller loop. So, this is the loop here. This fiber is straight at the end point. This fiber will form this loop. So, this is this portion and this one is this portion like this. So, finally, if we see finally, for I am talking about the fiber of same length. Finally, if you see this is a clamp, if we see the fibers, this is the long fiber, and our assumption is that fibers have chance to be caught at any point, okay, and all the fibers they have equal chance. And if you see the density of the fiber, number of fibers and versus length. Suppose this is the number of fibers and this is the length from the comb, this is the length. Okay. Here number of fiber will be maximum, okay, and then it will keep on reducing, and for this say cut polyester fiber, this curve will be, this is the fibrogram of cut polyester fiber, and for cotton the density, the number of fibers or density of fiber, density of the cluster is, because it is in a photoelectric method it measures the light penetration. So, then depending on the density. So, cotton it shows this is the nature. That means, the maximum length it is almost, it will be a longest fiber, but this curve it is called fibrogram. Okay. This we will discuss when we will discuss the fiber length. Okay. So, this is the length bias technique, and the assumption here is there are two main assumptions. One is the fiber, a fiber is caught on the comb in the proportion to its length as compared to the total length of the fiber in the sample. That means, fibers with higher length will have equal with higher proportion, but in our example we have taken for polyester, as the fiber, all the fibers have the same length, they have equal, all the fibers have equal chance, but in cotton longer fiber will have greater chance. That is the first assumption, and second assumption is that the point where it is caught is at random along its length. Okay. This is the, these are the assumptions. Based on these assumptions, we can, if we know this assumption, then we can actually take precaution to have know the actual fiber length. Okay. We will stop here today and we will continue with this in next class. Thank you.